right? So we are having this formula in this form, minus GH. Up to this point we have got, and similarly so on. What we get is minus G square H, so on, minus G power n minus 1 HK. G power n minus 1 H. G power n minus 1 H is, we don't have anything else, we have only K here. Now putting all this, the sum of all these is equal to 0. Now putting all this into picture, hope you all understand, you have understood this manipulation of writing this equation, this initial equation which we have. Firstly we will consider all the initial terms, right, and second we are going to come from the back, right, from the back one by one and get up to G power n minus 1 H. By considering first, H is common everywhere, H is common everywhere, the last terms of every equation, and then the GH terms of every equation, right, and similarly coming back so on and so forth, then we are left with only G power n minus 1 H, the last term, into K, right. So everything is a negative sign here. Now with this we can say that after getting into this equation, let me say what is our Cayley-Hamilton theorem stating? G cap power n plus alpha 1 G bar n minus 1 alpha 2 G bar n minus 2 alpha n minus 1 G bar plus alpha n into I is equal to 0. Let us consider this to be phi of G bar. Okay. Now consider this equation. Only this equation. Can I put this as phi of G? So when we can put this as phi of G, now this equation turns out to be phi of G, minus is common here, minus, and you can simply put this in this form. Just see this one, and we are finished with this, we are left over with this, minus H is a matrix, GH is a matrix, okay, then G power n minus 1 H, G power n minus 1 H into, what are the components that we are left over with? You can have this alpha n minus 1 H is a matrix, and we have this alpha n minus 1 K plus alpha n minus 2 kg bar plus alpha n minus 3 kg bar square plus so on plus kg bar power n minus 1. Right, the first term. Then we have the second term, alpha n minus 2 K plus alpha n minus 3 kg bar plus so on plus kg bar power n minus 2. We are reducing the number of factors and so on, we can get this as K. Okay, now we know that phi G bar, this is equal to 0. Therefore, from this equation we can have phi G is equal to this part. So without any problem I can just equate this to phi G is equal to this equation. Okay. Now since this is completely state controllable, inverse of this exists. Inverse of this is a controllability matrix, right? So controllability matrix, and since the rank of this controllability matrix is equal to n, inverse of controllability matrix exists. So without any problem, you can finally go for that equation. Now what is this? Now if I multiply this and just replace these values, what is this? If you can have QC, this is QC into, let me say for simplicity I will make this as 5G, this is QC, and this is some matrix X. Matrix, let me say it is some other matrix Y. So phi of G is equal to QC into Y. Now I need to find K, therefore I want Y here. So Y is obtained, QC inverse exists. QC inverse exists, and if I free multiply QC inverse here, QC inverse, therefore I get Y is equal to QC inverse phi G. QC inverse into phi G. Now what is Y for us? That matrix. QC inverse is this inverse and phi G is this one. Okay, phi G is obtained from the initial system, desired is initial original system. Now what is this? If I replace this, Y is that matrix. You can say alpha n minus 1 k plus alpha n minus 2 kg bar plus so on plus kg bar power n minus 1 alpha n minus 2 k n minus 3 kg bar plus kg bar power n minus 2 k is equal to h gh g power n minus 1 h whole inverse into phi g. This is the equation which you are getting. Now I want only k. I don't want to work out on all these values, though I want only k. So if I pre-multiply this with a row matrix which is of this form, pre-multiplying this, then 0 into this plus 0 into this, 0 into this, and 1. So I get the left hand side as k. So in this I can also pre-multiply 0, 0, 0, 1 into this one. So the left hand side what we got, k is equal to 0, 0, 0, 1 into h gh g square h g power n minus 1 h into phi g. Now this is we know this matrix, this is our state feedback gain matrix. Now we can go back and say, and this is also called as the Ackerman's formula. Which is used to determine the state feedback gain matrix from the original system to the desired system. Right? So 0, 0, 0, 1 and the controllability matrix, the inverse of the controllability matrix into phi of g, which is the original system characteristic equation, from which you can obtain the value of gain k. Right? So with this matrix, this finding gain k, we have seen two methods. Already we have discussed one method using the pole placement technique, right? And the other is the Ackerman's formula. And finding gain k is never unique, and we have different methods. We have 4 to 5 methods of finding out the gain k. You can also, if the order of the system is pretty low, then you can also go for direct substitution method, where k can be considered to be some scalar, k2, right, k3, so on. And if you substitute those values and just compare the powers of z, of the desired matrix and the original matrix, then you can obtain the value of k, so that you can find the state feedback gain matrix and make your system work in the desired locations. Right. So that is also one more method. You have many other methods, and we should be understanding that the finding gain k is not for a given system. The matrix gain k is not never unique. So it is the responsibility of the control system engineer to find out or take a trade-off between all these different types of methods and see which gain matrix is better to reduce the error close to zero. The error that is obtained must be going to zero, which is a much faster response. You require a much faster response. Therefore, that is what is required in this